first student. He became a postdoc later at the University of Illinois, where he worked with Fred Lamb, and then went to work with his identical twin brother, Don Lamb, at Chicago. And apparently this was a Lamb shift. And Cole has been with us at the University of Maryland since 1999. And today he's going to tell us about neutron star radii.
Great, thank you, Linda. Thank you for inviting me. This is my first trip to CITA, and I certainly had a lot of good conversations already. I will actually be here through Wednesday morning, so I'll be happy to talk with you. I'm in the visitor office. Yes, so I'm going to talk about something that I think is not necessarily on many of your minds, but I hope to convince you that neutron stars and their radii are of interest anyway. And I'm going to go through a few aspects of this talk. I'll give you a little bit of an idea of the life of a neutron star, the sort of work that it has to do in order to get to its maximum mass, for example. I'll begin not with the radii, but with masses, because I want to convince you that there are people in the community who actually are making progress and know what they're doing, so I can set up the issue of the radii, where there are very profound uncertainties and systematic errors that we have to deal with. And I will try to be as honest about those as I can, but I also will give you what I think is a somewhat hopeful suggestion about some methods in the future, including right at the very end, I'll discuss a little bit about gravitational waves and the sort of information that we might hope to obtain from the next generation of detectors when they see these sources. By the way, please do feel free to bring up questions or comments during the talk, and if we have a really good discussion, then I will adjust and move on. The kinds of things that we have to think about as our most significant challenges here in measuring neutron stars, which, as I will explain, has great potential for generating insight into nuclear physics. Can we measure neutron star radii without huge systematic errors? When I get to the point where I discuss the radii, I will explain why this is tough and why some of the methods you might imagine are very straightforward and easy really do not work at all. Therefore, we have to go to more sophisticated methods. There have been discoveries of neutron stars within the last few years, including one just mentioned last week, of about 2 solar masses. And this turns out to be important and meaningful in constraining the nature of matter in the cores of neutron stars, but are there others that are even heavier out there? Can we find ones that are even more massive? And if so, what will this tell us about those systems? What can we do with future satellites, X-ray satellites, or what can we do with gravitational radiation? So these are the sorts of questions that I will discuss throughout. Now, by the way, just so we can get one technicality out of the way, in astronomy especially, hypotheses are tested in bundles. This means that when we are measuring some aspect of a neutron star, even if its mass, radius are known to high precision, and we want to go from that and say, well, what exactly does this mean in terms of the interior state? We have to realize that we are making ancillary hypotheses. For example, that general relativity is the correct description of gravity even for neutron stars. And as various people have suggested, here's some work by Mariano Orellana, if you add bells and whistles to general relativity, you can change some of the aspects. For example, I'll be showing a lot of mass versus radius diagrams, which is a way of characterizing neutron stars and get at some of the interior composition. But it turns out you can shift these around depending on what you're adding to GR. Now, this is something to keep in mind. However, I will optimistically say that in a few years, when advanced LIGO and similar instruments start making their detections, it is likely that especially double black hole mergers, if they conform to our expectations, will test GR in the strong gravity limit. So I'll say we're going to go with GR for the rest of the time. Now, for those of you who may not have experienced the sublime transcendent joy of neutron stars, I want to put up this figure by Donny Page of UNAM in Mexico as an indication that neutron stars are a smorgasbord of extreme physics. And so if you are interested in strong gravity, strong magnetic fields, and weird condensed matter phases, these are the objects for you. They have the highest density in the accessible universe outside of black holes. They have the strongest magnetic fields in the universe. They have temperatures that are tens of millions of degrees. They are, in their interiors, superconducting superfluids with a transition temperature of 1 billion degrees Kelvin. They have bizarre nuclear phases called the antipasta sequence. So lots of fun stuff. The thing we're going to focus on, however, is the giant question mark in the middle. This is where you have the core of the neutron star, and the composition of the core is unknown. Now, I'll tell you basically why that is, and then I'll tell you some of the possible candidates. The issue is that this matter is several times nuclear saturation density, so atomic nucleus density, but is cold in the sense that its temperature is much less than its Fermi energy. That means we cannot simulate this in laboratories. In addition, it's also a very asymmetric state of nuclear matter. There are far more neutrons than protons, otherwise they'd be proton stars. So with all this in mind, it means that nuclear theories actually have wide divergence about the predictions of the state of matter. Although there is good understanding up to nuclear density and maybe a little bit higher, when you get to these densities with this kind of excess of neutrons, the dominant composition, depending on your theorist, could be nuclions. So neutrons, protons, with a smattering of electrons and muons. Maybe it's quark matter, or strange matter, or condensates, or hyperons. There's a large disagreement about this. Nuclear physicists fight about this all the time. And since we can't explore this in the laboratory, we have to look to neutron stars themselves. However, the issue is, probably for the overall good of humanity, we cannot experiment directly on neutron stars. We must therefore instead look at the indirect indications, their mass and radius. So here I have gravitational mass versus what is actually circumferential radius. I probably don't have to say that in a GR-heavy department like this, but notice that this is not the same as the baryonic mass. The baryonic mass is what you get by taking all the particles separately and weighing them. This is what you would measure from a distant satellite from Kepler's laws. Gravitational mass is less by maybe 20 or 30% because of the large amount of binding energy. This is the circumferential radius. Draw a circle around it, divide by 2 pi, as opposed to starting in the center moving out. So if you look at, here we have just 6 candidate equations of state, nucleonic, strange star, quark matter. This one has a pion condensation here, so it leaks over to smaller radii. If you are able to measure the masses and radii of a whole bunch of neutron stars, then you can imagine mapping these out and getting great insight, and at least constraining things very well. If you cannot measure both, and I'll show you why radii are tough, the maximum mass is helpful because clearly, at least from this set, if I have something that's, say, 2 solar masses, it'll rule out all of the ones that cannot reach that high. A fundamental thing to emphasize here is that it is believed that all neutron stars have the same fundamental equation of state. So if you have a neutron star which cannot be accommodated by one of these, that is ruled out as an equation of state for all neutron stars. So this is an important constraint we can apply. The basic argument is neutron stars are cold but have a high Fermi energy. High Fermi energy should allow them, if necessary, to tunnel to the actual ground state of matter. So that's why you're not expecting differences in the equation of state between different neutron stars.
I have a question.
Yes?
I'm not sure about the separation between gravitational and nuclear. There is no self-interaction in GR. The mass of a black hole that we measure at infinity will be equal to the mass of all the protons that we dumped in.
So gravity, the gravitational potential energy is negative. So if you have something that's a very compact grouping of your objects, then it will have a lower total mass. Another way of saying that is if you collapse the matter to form the neutron star, then it releases energy, largely by neutrinos in this case.
But that's not how, you take 2 neutrons, you have 2 protons, you make a black hole out of them, and at infinity you measure 2 of them.
No, so if you were to take matter and drop it straight into a black hole, then you would be able to add that total amount of mass. But if it spirals in and releases energy in the form of photons or something, the total mass added is less than the mass of the individual particles at infinity. So in this case, it's a 20 or 30% difference. So let me now tell you a little bit about neutron stars, masses you'd expect, because as I said, we are going to discuss masses and what maximum masses we should find. So what is the initial mass of a neutron star? This initial mass, the only way that we know how to form neutron stars is by the core collapse of a massive star. Of course, you do work on that here. If you take sort of the standard idea that you need to get to something like the Chandrasekhar mass and an iron core to have that collapse, there are some modifications to that. The baryonic mass, the sum of all the component particle masses, is 1.35 or so. But collapsing this gives you a gravitational mass of 1.2 or so. So keep that in mind. It's not obvious how you get an initial mass much less than this. There could be some fallback. There's some mass cut in the pre-supernova star such that inside the cut the matter makes it to the star, outside maybe gets blown away. So it's unclear exactly how this falls back. It may be that there's enough fallback that leads to a black hole and collapse. Although it's also possible that black holes are formed largely by the whole star going in. But if we're thinking about the maximum mass that we can get, we're not going to stick with only what we can have with the formation of the neutron star. There's also the possibility that the neutron star is in a binary, and that mass can be transferred from the stellar companion to the neutron star. And for this, by the way, I want to emphasize that the accretion from the interstellar medium is minimal, always. It can be completely ignored. So we're thinking here about a binary, and there are two types, as there always are in astronomy, and this is defined by companion mass. So you have high mass X-ray binaries, and for these, the only stable way to transfer mass onto a neutron star is from the wind of the high mass companion, which manages to get onto the neutron star or black hole. This actually transfers very little mass. It's not because the companion is low mass, it's high mass. It transfers very little mass because high mass stars do not last very long. The time scale is often much less than 10 to the 7 years. It is the path for double neutron stars, which we'll talk about in a second, but the total amount of mass that's transferred is much less than 0.1 solar masses. In cases where it's been estimated, it's often more on the order of 10 to the minus 3. So it's really a very small amount of mass that's added. The other possibility is that the companion star, instead of having maybe 10 solar masses, is low mass, maybe less than a solar mass, maybe half a solar mass. In this case, you have Roche lobe overflow, so you have the companion close enough that matter flows over the inner Lagrange point. And this can last a very long time and can, theoretically, in the lifetime of the system, transfer almost the entire mass of the companion. So half a solar mass, 1 solar mass. And so the example here that I've used, which you may be able to see, this is Norman Schnesena's favorite system for the 1820 minus 30. It's a very compact system, 11.5-minute orbit, and as has been demonstrated by excellent scientists, is unquestionably in a triple system. And we're actually going to reach this guy later, because it's going to turn out to be one of the systems claimed to have a strong radius constraint. So this is the way the star can acquire additional mass after its formation, and the net result is that, broadly speaking, a neutron star's gravitational mass can go from maybe whatever minimum mass is possible from a core collapse, 1.2 say, to whatever the maximum mass is for a neutron star. We don't know that. The range that is possible, it could go up to 3 solar masses if you really stretch it. Now, by the way, if you have a rapidly rotating star, its centrifugal support could in principle increase the maximum mass, but in practice, all the ones that we currently see spin too slowly to change this significantly. And to give you an idea of the extremes we're talking about, too slowly is 716 hertz. That's the fastest spinning neutron star known, but even that is insufficient to make much of a difference.
So if you were close to breakup, how much would it change?
If you were close to breakup, you could change it by tens of percent. Yeah. But even a fairly small magnetic field, when you're getting close to breakup, would be able to spin things down in a relatively short amount of time. You can get even higher masses temporarily from the merger of two neutron stars if you have differential rotation inside, but that really gets stopped within probably a few milliseconds. If we're interested in masses, we need to know how this is going to be done. And much of my discussion here is drawn from what I consider a very well-written review by Paulo Freire. This is Astro pH thing from 2009. We're going to begin by thinking about kind of the simple mass constraints that are used in ordinary circumstances. Normal double stars, extrasolar planets. And the basic idea, as you may recall, is if you are able to look at a star and see that its speed, its line of sight speed to you, is changing periodically. For example, you might look at spectral lines, or as we will see, if you have a pulsar, you might be able to use the timing. If you measure the period and the speed amplitude of this oscillation, you can generate something called a mass function, which here is constructed purely from the observables, and here is related to the masses and the inclination. M1 is the mass of the star, which you don't know, which you're looking at. This is the inclination angle. 90 degrees is edge on, 0 is face on. And if you gaze at this, you can eventually see that this measured value is a strict lower limit to the mass of the star you're not looking at. But it depends on a couple of things we don't know in general. One is the mass of the thing you are looking at. For example, if you have a very massive companion, for example, the companion to Cygnus X1, this is a large enough value that it will lower your mass function. If you have an inclination that is unknown, then you could, in the limit, get to an infinite mass if you were nearly face on. So you'd like to be able to have other ways of measuring these quantities. Ideally, you'd really love to be able to have enough measurements that you can not only get the masses, but actually constrain the underlying theory. And as you may know, this is possible with pulsars because they're such good clocks. In this slide, I'm intending to awe and intimidate you with my latex skills and to list some of the so-called post-Keplerian parameters.
Not very good. Those equals are well away.
I failed in my intimidation. So it's possible to measure quite a few additional quantities beyond what you would in non-relativistic systems. This is the pericenter precession. This is the Einstein delay, where if you have an eccentric orbit, then at pericenter you're moving faster and deeper in the gravitational well, so that changes timing. This is the orbital decay due to gravitational radiation. And here you have the range and the shape of the Shapiro delay. So the idea is, suppose I have a double system, say 2 neutron stars, so they're theorist point objects. And one of them is a pulsar. And if I have the pulsar here and the other one, from this standpoint, it just comes to you directly. But from the other standpoint, it has to pass close to the companion. And so you get delays as a result of going through the gravitational well. Now the range and shape, well, the range depends just on the mass of the companion, not on its nature, not on how compact it is, not on tidal forces. It's a purely relativistic effect, no classical contribution. The shape is how does this change over the orbit. For example, if it's face on, there will of course be no change in the orbit. If it's edge on, truly edge on, you'll have a cusp in the point of the orbit when it goes right by the companion. There are enough observables here that you can indeed constrain the system, constrain the model, constrain general relativity. And this is the reason why the Nobel Prize in Physics was awarded in '93 to Halson-Taylor. Oh.
I'm impressed by the number of digits for T-sum.
Yes.
Is known well enough for the sun?
No, G isn't, but G times the mass of the sun is known well enough. Independently or not, the product is. Yeah, it's one of these remarkable things that we get from, we can measure the motions of planets very, very accurately, but not G. So double neutron star systems are indeed the perfect case because they're point-like. No classical effects, tidal effects, who knows what else. In addition, because to get a double neutron star system, you have 2 supernovae, the second one typically leads to an eccentric orbit, which allows you to measure pericenter precession and the Einstein delay. Precisions better than a part in 1,000 are possible, so this is the level to which in weak gravity, general relativity has been confirmed. As an example of this, I will show you a figure from what was at the time the only known double pulsar. It is now a single pulsar because one of them is precessed out of our line of sight. And one way of showing the agreement of all these effects is we plot them on a mass versus mass diagram. So here we have the pericentric precession, the range and shape of superior delay, the Einstein delay, the decay of the orbit. If the underlying model is correct, these constraints must all intersect, and indeed, as this inset shows, it does. The fact that it is so close to this end of the wedge is one indication that this is a very nearly edge-on system. So it's kind of good luck in that sense. So these are superb systems, and obviously the first ones you look to in terms of mass measurements. If you want to get neutron star masses, these are the systems you look at. So when you do this, you turn out to get very tightly clustered masses. So here we have something that's a bit more extensive than just the double neutron star systems, but all the ones that have PSR in them are, and you see especially these, which look like they don't have error bars, actually do. They're part in 1,000 measurements. They are the most precisely known masses outside the solar system by a good deal. Well, people noticed, say, 10 plus years ago, gee, these are really tightly constrained. Very close. 1.35 plus or minus 0.1 solar masses. Gosh. Not only that, but as I said earlier, because neutron stars come from massive stars, and so you had the original neutron star, then maybe in a high mass binary, there's almost no mass transfer. So these are essentially the birth masses that we're talking about. There was a lot of work in which people proposed that, in fact, this might indicate that there is a low upper limit to the masses of neutron stars. Maybe it's only in this range because 1.5 is the highest neutron star mass you can ever have. And this would be cool. It means you have a kaon condensation or some other phase transition that might do this for you. However, people also reminded each other through this time that you have another effect. You run into it all the time in astronomy. You have a selection effect. The selection effect in this case is not so much observational as that to get a double neutron star system that is close enough that you can measure all these effects, you have to go through a very particular evolutionary channel. So maybe it just is the ones in this channel that happen to have these masses. And indeed, 3 years ago, again last week, there have been neutron stars detected that are about 2 solar masses. Far, far away from this apparent tight cluster. These are both systems that have a neutron star and a white dwarf. Now, people have known of neutron star white dwarf systems before, but in terms of mass measurements, these are not great. The problem is that for some of the effects we are talking about, there are classical contributions. For example, if you have a neutron star white dwarf system, the pericenter precession can be affected by tides. So you have to worry about that. However, in both of these cases, there are specific things that allow you to get around that. One is that the original 2 solar mass star, by Demarest et al., is almost an exactly edge-on system. And so this is what the Shapiro delay looks like. Very cuspy around the point where you have conjunction. And this, by the way, is important because if you have something that is not almost edge-on, but 60 degrees, you get kind of a very gradual effect that is degenerate with eccentricity of the system. So you can make this measurement. You find it's 1.97 plus or minus 0.04. But recently this record was broken by another white dwarf neutron star system where they were able to see spectral lines on the white dwarf. And so by getting a mass ratio, they were able to figure out this is about 2 solar masses. Now, a cool thing in terms of these high masses is that for other reasons entirely, it is very possible that this is just the beginning. The issue is you cannot assume that every neutron star system is going to be edge-on to you. That would, well, I guess that would really be news if it were true. So you'd like to be able to measure the Shapiro delay, which is a very subtle effect, with systems not so extreme. To do this, you need excellent timing capability for your pulsars. This is being developed very actively and rapidly by multiple groups around the world because for millisecond pulsars especially, which are short period and have low magnetic fields and are superior clocks, these are being thought of as useful for a pulsar timing array gravitational wave detector set. You're using nature to detect gravitational waves of the 1 per year type of frequency. So it may be that these improved timing techniques will give us more of these. We'll see. Well, what does all this mean? So I said, of course, I'm going to begin this talk. I'll discuss masses, and so here we'll wrap up masses. These indications of two solar masses plus tell us that obviously the ones that can't sustain that are dead. These are not the only equations of state that have been presented, otherwise we have a unique winner here, of course. Nuclear physicists, indeed, are clever, and like astrophysical theorists, are very, very difficult to kill. So people who are interested in hyperons or quark matter or whatever are able to get around these constraints. So to back up a little bit, I say here, it may suggest a hard equation of state, small contributions from exotic phases. The reason this is relevant is, suppose you have matter which in its ground state goes from being mainly nucleons, neutrons, protons, whatever. Then you increase the density and it goes through a phase change, phase transition. It does this because whatever the new state is, hyperons or quarks, is lower energy than the previous state. This means it is more easily compressed than if it did not have that transition. Being more easily compressed means smaller radius for a given mass. Also means a smaller maximum mass because gravity becomes dominant earlier. So the classic argument was that get to a high enough mass and exotica, hyperons, quarks, are disfavored, but not at two solar masses. 2.2 or 2.3 is now the current bar that we are being told, and we'll see. That may be legit, but I'm sure there are ways around that as well. But what we really want is radii. And the reason is that, although I'm not showing it here, if you take the selection of equations of state that can manage two solar masses, there's a really broad range of radii. Notice that for many of these equations of state, there's a wide range of masses with about the same radius. That characteristic radius for ones that can make two solar masses goes from about 8 to about 16 kilometers, factor of 2. So you really would like to know radii. This is the frontier. But it is a big challenge. Fundamentally, the reason is, unlike mass, which you can measure from its effects on things that it isn't, orbits, radius does not have effects on things, particularly. And the ways that people propose suffer from large and often very unknown systematics. I will give you an example. Consider how you might want to measure the radius of a mean sequence star. The sequence you might follow is, you measure its flux, you measure its distance, now you know its luminosity, then you can take its spectrum, say it's a black body, you get its temperature, you're done, you have the radius. People have done this with neutron stars. The answer they get is on the order of 5 kilometers. That's way too low. It's at least a factor too low. So what's going on? Even though the spectra are pretty close to black body looking, they are not black bodies. They are Planck spectra that are inefficient emitters. The inefficiency, it could be that you're only 20% efficient. There are very scattering effects that can do this, but the point is you can't just use a simple black body. This means you have to put in hard work in order to get the details necessary. So that's why it's not just a trivial thing to do. So I will now describe a few such methods. I'll describe, I guess, one in particular that has been used a lot recently, which, if you take it at face value, gives you excellent constraints, but where there are strong indications of systematic problems. Then I'll talk about a couple of methods that we're working on that may be useful for future large area X-ray detectors, because you need a lot of information. And I should say that one of the key aspects, one of the key difficulties about a lot of this is there are no neutron stars known that have surface atomic line features. There are some claims out there, but none that are known for sure. So we do not have the wealth of information we do about many other objects in astronomy. In continuum spectra, well, to quote the immortal Monty Python, continuum spectra of this type all are small at one end, big in the middle, and small at the other end. And there are a lot of characteristic spectra that can do that, and making inferences from them is tough. So I will begin with a method that was originally proposed by Jan van Paradijs in 1979. This involves thermonuclear X-ray bursts. You have your neutron star, it's got a companion. Companion is donating mass. That mass is mainly hydrogen and helium, of course, and it can pile up, and under the right circumstances, the layer that is accreted can become unstable to nuclear fusion. So it's not stable fusion. It actually is something that often lasts for a few seconds, is close to the Eddington luminosity for that time, consuming the matter that it deposited over hours to days. There are occasional ones that last much longer than that, hours at the same kind of luminosity. So in the former case, this is probably a helium ignition, a shallow layer, shallow meaning density is 10 to the 6 grams per cubic centimeter, which is practically vacuum by neutron star standards. And then the longer lasting ones are believed to be permanent ignitions in much deeper layers. They have to accumulate over a year or two. So how do you use this method? Well, you have that basic philosophy there. There are some types of bursts which show various characteristic spectral developments indicative that they are close to or at the Eddington luminosity. Essentially, there is a photospheric radius expansion, so the characteristic temperature goes down in the middle of the burst. If you take those and you say, all right, we've got the Eddington luminosity here, and if we know the distance, then the flux and the distance give us the luminosity. If we know that's Eddington, then this gives us the mass if we know the composition. You might measure the temperature to get the radius, and so you're set. There are some key assumptions here, as there always are. For example, you assume that you know what the spectrum is. I mentioned earlier this difficulty, maybe unexpected. It makes it tough to know exactly how to treat the spectrum, but people have sophisticated model atmosphere spectra that might work. And you assume you have uniform emission over the whole surface. Well, when Van Paradijs proposed this, the instrumentation did not exist in order to get enough information. But with the Rossi X-ray timing explorer, may it rest in peace, you had a large area instrument, 6,000 square centimeters, that could collect a lot of data. And as a result, starting a few years ago, the group at Arizona, led by Ferrer Ozel, decided to take another shot at the Van Paradijs method. And they did the logical thing, which is to start out by assuming that all the assumptions are correct and there are no systematic errors. What do you get out of this? Well, here again, we have our friend 4U1820 minus 30. This is in a globular cluster. This means it's much easier to figure out the distance to this source than it is to most, and so that is a big plus. And they do their analysis, and my gosh, look at this. Here's the gravitational mass, circumferential radius. Here's some of these candidate equations of state. And here we have their constraints. This green part of this 1 sigma, this light blue part is the 2 sigma. So we're talking about a 1 sigma uncertainty in mass and radius of 4%. Absolutely remarkable. Really, if we could rely on this, it would eliminate almost all equations of state. It would be fantastic. But these small errors are profoundly misleading. This is something that was pointed out. There's a little discussion at the end of this paper that really pointed out by Steiner et al. In 2010. Here's the issue. You have your measurables. The measurables include things like the flux when you think it's at Eddington. You have the color temperature. You have a couple of other things. To get mass and radius out of this, you have equations that you solve for M and R. Those equations involve square roots. And the quantity inside the square root, I'm pretty sure we're agreed, should be non-negative. Or to put it another way, if it were negative, that would be even more major news about the nature of neutron stars. But the problem is that if you take the observables and their uncertainties as a probability space, only about 10 to the minus 8 of that space gives you non-negative values for the quantity of root. So the reason that we're actually getting this extremely tight constraint is that it's basically only at the very tail of the distribution you can have legal values. And so only those are giving you answers.
So did they just do their statistics wrong?
No.
And then they're one of these uniform deviates where it can't go negative.
Oh, no. I mean, so they had their distribution and they simply only took the legal values.
Right, so they did their statistics wrong.
If this is to be representative of what they actually think the source is, yes. But if it's a matter, and they were not quite clear in the description of this, if it's an issue of saying, what do you get if you just make all the assumptions, then it's a different story. And Steiner and others afterwards have emphasized this, and what it really tells you is that there are systematic errors. There are aspects of the assumptions that can't be right. Now, as it turns out, one of those aspects, and this is something we discovered, is that the spectral model they were using is a terrible fit to the best data. So this is something you might worry about, and I'll talk about that in a second. So you wonder, are there models that might fit well to the best data? And what can you say using those models about the assumptions, for example, the uniformity of surface emission? It turns out that there is a group, Valery Sulamanov, Yuri Putanin, who have done some recent and very careful work about the spectra of sources in X-ray burst states. Right temperature, right composition, all that. We used data from one of these super bursts I mentioned. These are the hours-long things that are still at the same peak luminosity. This particular one, near the peak temperature, has 800,000 X-ray counts. For those of you who don't work in X-rays a lot, that's a lot of counts. So we're not Keck, we actually count our photons, and this is a lot of the count. And this is actually an extremely good fit. There are your residuals in essentially sigma. So this was very encouraging to us. By the way, the model that had been used previously had residuals in sort of the 10 to 20 sigma region all over the place. So this is a model that works, at least works pretty well. And indeed, we took the superburst. Remember I said these last hours. So we initially looked at just the segment at peak temperature, and that actually did a fit over 1,600 seconds, almost 20 million counts, where we were allowing the temperature to vary, but the surface gravity and redshift or whatever had to stay constant. And what we found is that the best fit is actually statistically good. We have this many degrees of freedom because we have many different segments. A phenomenological model like a Bose-Einstein is actually much worse. So this is the point where we get greedy. So now that we actually have a model that fits, can we do something extra with it? Can we take this information and learn even more about the system?
In which part of the spectrum are you getting constrained the composition, and in which part of the spectrum are you getting constrained the integration?
Oh, okay. So the effects, so this is primarily dominated by scattering because it's high temperature. So the Eddington ratio is, so there's a combination you get between the surface redshift and the Eddington ratio. The composition is mainly down at the low end because this is where free processes become a little bit more important compared to scattering. So these are very subtle effects, which is why you have to have enormous numbers of counts to get anywhere.
So you think there's a convincing affection of helium
The helium atmosphere that we fits a lot better than a pure hydrogen atmosphere or a cosmic composition. But it is also true that if you have a little bit of hydrogen, you can add it on. And we haven't done enough to know how much of a serious systematic error we introduce. One of the first things you'd want to do is know whether these excellent models can be used in the Van Paradijs method and just give you the answer properly. Maybe it opens up parameter space. But in fact, what we found when we did our fits with this superburst is that the fit emitting area actually changes with time, drops by about 20% as this burst goes out, the superburst. And by the way, I'm normalizing it to 1, not because I think that the whole surface is emitting there necessarily, but just because I want some normalization. It may be that never does the whole surface emit. Therefore, the issue is, if in this case where you can really tell the assumptions don't work, why is it that you should assume that when you have shorter bursts where you can't tell they do work? So that's a problem. Something that was suggested by Machina and Madej a few years ago is maybe if you get a really good fit, and all these subtle spectral things can allow you to constrain both the surface gravity and surface redshift independently. And if you did that, then you would be able to get mass and radius because there are different functional dependencies. We can't do that yet, but what we can do is, for a given surface gravity, constrain the surface redshift. So there's kind of a line that you're going to see in some figures I'm about to show you that will do this. So this is something for the future, for an instrument maybe 10 or 20 times the area of RXDE, to be able to catch one of these things. We really need a lot of counts. It does have the advantage that the systematics are at least different from some of the other methods. A method that I've been focusing on recently with my collaborators is a different approach. We know from looking at a number of these X-ray bursts that the emission is not just this sort of smooth rise and drop. In fact, there are also brightness oscillations, which have been interpreted since they were discovered in '96 as a hot spot on this neutron star rotating with the star, maybe the burning region, or maybe the region that is just hotter at this instant. Now, these things rotate a few hundred hertz. This means the surface equatorial rotation speed is 10 to 20% the speed of light, so there are special relativistic effects. And the high gravity means there are general relativistic effects, like light deflection. Thus, at least in principle, the light curve you get, the details of the oscillating intensity of the X-rays, could give you information about mass and radius. So there have been a number of papers about this. Here, if you're interested in the geometry, you've got different angles to the observer, angles between the spot and the pole, and things like this. But the challenge is you have to deal really carefully with degeneracies. What I mean by this is, suppose that you have a particular case, a particular neutron star with your hotspot, and you see a light curve that has modulation, but it's fairly low amplitude. Why is that? Well, maybe it's because the spot is very large, covering almost the entire star, so you have low amplitude. Maybe it's very small, so its flux is small, so you have low amplitude. Maybe it's because the spot is nearly centered on the rotation axis, so you have low amplitude. Maybe you, the observer, are close to the rotational axis, so you have low amplitude. Maybe it's a very compact star, so light deflection gives you a low amplitude. So all of these mean that it's necessary to do a very detailed study of the degeneracies and how you can get around them, and whether it's even plausible to do so even with the next generation of instruments. And recently, work led by Kaho Lo, who is a graduate student finishing up with Fred Lamb at the University of Illinois, we put together our paper, and so I will describe this now, our analysis procedure and some of the conclusions we reached. We considered an instrument that might be 20 times the area of our XTE, because this is what is being planned for European missions such as the Large Observatory for X-ray Timing, LOFT, or the US-based AXTAR mission. And this is the theorist's favorite of generating synthetic data, analyzing the data, demonstrating you can more or less recover what you put in, and then, we hope, trying to give a reasonable understanding of some of the systematics so we're not too misleading. And we're using various Bayesian methods to analyze joint posterior distributions in our parameter space. And then ultimately trying to boil this down to mass and radius. Because some of the parameters that we have, and here we have a list of them, so spot inclination is not of tremendous interest to us, or the observer's inclination not so much, spot size and shape. So all of these things come in order to make the ultimate light curve. And we're talking typically about, maybe a slightly more massive neutron star than average, and a 12-kilometer radius with a couple of different rotation rates. We're also trying to be as realistic as we can in the context of the synthetic data by imagining that there is, in addition, background emission not related to the spot. This makes a big difference, especially if you have, say, 1 million counts from your hot spot, and maybe total of 10 million counts overall. This seems actually realistic, given some cases that we can see. In other cases, maybe you'll have a background about equal to your hotspot counts. That also can be realistic in some circumstances, and then for something to be fairly low. Now, we went through a whole bunch of aspects of this, different rotation rates, different inclinations. For example, if you have the observer and the center of the spot on the rotational equator, this is optimal for the analysis that you do. The reason is that you get a lot of your information out of overtones. And if you have something on the rotational equator, it's moving as fast as it can, and it's going to give you the largest amounts of aberration and beaming from special relativity. On the other hand, as you move the spot center close to the rotational pole, at the pole you have no modulation whatsoever, and even a little bit away, the modulation is not only weak, but you also have very little in the way of harmonic structure. This takes away the information you can get. So we essentially did a whole bunch of analyses, and our work was as thorough as we could manage it. So I'll give you some of the highlights that we had. Now, in the following set of diagrams, I'm going to show you always gravitational mass versus circumferential radius. The cross here, which is kind of hidden, is the actual location where we injected things. The star is the maximum likelihood point. The dotted region is 1 standard deviation. The solid is 3. Here's our chi-square of degree of freedom. And this, you may remember I mentioned earlier that we found that from the spectrum, we would be able to constrain the redshift given a surface gravity. This is that constraint on the MR diagram. So in other words, if we had extra information, we could cut in. So in this particular case, if we have high background, so number of counts in the background is 9 times the number of counts from our spot, we get a good 1 sigma constraint, but there's a fairly extended 3 sigma region. If instead we have a low inclination, so not 90 degrees, but 20 degrees for the spot center, these are our constraints, which are hardly worth writing home about. Now there are neutron stars, by the way, that are known to have harmonic structure in their light curves. This would not. This is something that would look just like the fundamental. You get virtually no info. But something like this, you are able to get info. There are other things we examined as well. Suppose that you have extra information about the system. Not so much as to be unrealistic, so not that you know everything but the mass and radius. But there are cases where you can measure the observer inclination by techniques such as ellipsoidal light variations that have been very successfully used in black hole systems. So the comparison here is, you start again with our rotational equator case, with a very high background, so this is what you just saw. And now you imagine that you know the observer's inclination. And as you can see, there's a huge difference in how well you can constrain the mass and radius. In addition, you find that if you relax some of the assumptions we had, but analyze it as we did anyway, so we assume a filled circular hotspot, maybe it isn't, maybe it's extended in some direction like east-west, then you increase the uncertainties. This is a medium background, so you compare it with something small like this. You increase the uncertainties, but you have a tiny little bias. This is not too bad. And something I will reiterate in a couple of slides is, we found that there was no combination of violations of our assumptions that would do the following 3 things at the same time. That they would apparently give a good fit in the chi-square sense. They would apparently give a tight fit in the size of the region sense, and that they would be significantly biased. So if this holds, it suggests that if we have a future analysis that appears to show a good tight constraint, it's probably pretty high. Now the last thing, for those of you who have been patiently waiting for gravitational waves, is another aspect of radius estimates, for which I have optimism and enthusiasm when advanced LIGO and successor instruments start detecting things. As I'm sure you know, ground-based gravitational wave detections will likely happen in the next few years. Science runs in the next couple of years, 3 years maybe. And then as the sensitivity grows greater, detections and characterization. Now the idea is, suppose you have 2 neutron stars that spiral together. Far apart from each other, they act like point masses. Closer, they are tidal effects. These tidal effects cause their in-spiral and gravitational waveform to deviate from what you would expect if you had 2 point masses. So there's been a lot of study about whether this could be used to determine quantities such as the radius or the Love number of the neutron stars, which would be very helpful indeed. Now the thing is, you're going to need high frequency sensitivity in order to do this, because it's right near the end. And people have talked about ways of doing this, for example, with phase squeezing of light. And if you look at some of the work that has been done fairly recently, Analytical suggestions are that for something that has a signal-to-noise ratio which at 16 is about twice the threshold for LIGO, so 1 in 8 events would have this, they can actually distinguish between big fat neutron stars and small compact neutron stars. This is, however, something that needs a lot of work from the numerical relativistic standpoint. There's been some confirmation, but there are a lot of effects, nonlinear fluid effects, for example, that could have changed things nearby. So this is something that still has to be examined, but it's promising, and at a very minimum, it will have extremely different systematic effects than the X-ray measurements. So I think really collectively what you have to do is bring together all these methods and see whether there is agreement. Because in each case, you might be able to point out, well, gee, I'm not sure about some assumption. So my conclusions are that the precisions of these measurements could be fairly high if you have hot spots near the rotation equator, and there's decent evidence for this in a couple of cases. And it can improve if you know extra information. I want to highlight this again. This is key. The nightmare would be apparently strong constraints and a good fit that are horribly biased, because then you couldn't trust them. We have not found that combination. This may be a good sign. So I think future large area X-ray instruments may indeed be able to tell us a lot about the radii of neutron stars, and of course, we're certainly also hoping for gravitational waves. Thank you.
Thanks. Cool. Questions?
There has been some recent measurements by the Montreal group of British neutron stars was giving, I think, 9 kilometers.
Yes.
Any comment on that?
Yes, 9 kilometers is extremely challenging to do if you also want to have a 2 solar mass neutron star somewhere in the universe. Being that compact is tough. I looked very carefully at those work. This is Sebastian Guillot et al. I looked very carefully at that work, and I think they did a good job of expressing what they did. But the sorts of systematics you could worry about are not only the spectral effects, like are they using the right spectrum, which I mentioned, but also is the whole surface emitting. Now, if there were a hot spot, you might expect to see oscillations, and you don't. But there are some ways, especially for rapidly rotating neutron stars, where you can imagine that there's a temperature as a function of latitude. If you did the analysis, and that were the actual situation, you would infer a smaller radius than it actually had. The other thing, and I think it was a good call on their part, but could introduce uncertainties, is they assumed that all the stars they looked at had actually the same radius. And they use this in order to tighten their constraints. And there are regions where the radius is nearly constant, but if there's a wide range of masses, that might not be a legitimate assumption.
So I'd like to follow up on my question. You keep referring to the gravitational mass as being different from the total mass, but they're not. By equivalence principle, they are the same. If you take 2 neutrons, you make a neutron star of them, this neutron star will affect gravitationally the motion as 2m neutron. No corrections. That's the point of GR.
So
there's interaction energy, but the mass is 2m.
The issue here is, suppose you take 2 neutron stars and you hit them at each other very rapidly. So they're hot, and they cool off by emission of photons. So the total mass of the neutrons and the photons is the same as before, but no, it isn't.
The mass is the mass. You take 2 neutron stars, you merge them, the mass will be 2m. The energy is different. There's interaction energy.
Oh.
The mass will be 2m.
No, you're actually losing energy to infinity.
You're losing energy, but you're not losing mass.
But energy gravitates too.
But it's the mass that defines the energy. You cannot define the energy of a black hole as an integral over free space.
Luckily, I'm talking about neutron stars.
Mass, but
no, the total gravitating mass involves energy as well as mass. It loses energy in the form of neutrinos and whatever to infinity. So when you're around it, the mass
self-interaction in gravity.
Strong interaction, strong equivalent.
Why don't we ask,
We find out this
M,
later.
it's M. It's the same M that enters everywhere.
How about we continue this
There is
upstairs
an
over
issue, but the M is the same.
Let me ask another question.
Good, let's ask another question. We can continue this upstairs.
So you found that in your simulations you found a bias, a small one, but a
A
bias.
small bias if the spot shape, instead of being a circle, is essentially 3 circles next to each other. So a very large deviation in the spot shape.
Yeah, okay. So you know the origin of the bias. In other words.
Yes.
Yeah, okay. And the problem is that in real life, of course, you don't know what you put in, so you can't figure out what the bias is.
That's
There's no sort of other signature you can see that you can detect whether you're getting.
I think that one would be pretty tough. There are other types of violations of our assumptions we put in to see the effects. And one of them that had very little effect we were happy to see is, suppose instead of being a dilute Planck function, so Planck without 100% efficiency, suppose it's a Bose-Einstein with the chemical potential equal to minus kT. So pretty significant deviation. We actually don't get a significant bias. It's able to accommodate that and get a good fit anyway, and without bias.
Yeah. So I mean, your statement was that you didn't find any, whatever, degrees of freedom where you got a big bias. But that's just a
Oh, sorry. We found some with big bias, but not the combination here of good fit, tight fit, and bias.
I see.
So for example, let me go back to this
Right,
case.
well, it's a small bias compared to the errors, but yeah.
That's right. So in terms of the best radius versus the actual radius, it's a large shift, but it's not statistically significant, and in any case, there's no significance to it. Yeah, Chris.
Sources that one can do both the thermonuclear flash spectral fitting and the post-outburst cooling emission.
So people have tried that. There are a number of the transient sources, for example, like SATS-J to the wave, where people have worked on that. And there are suggestions, which may be correct, but the jury is still out, that doing this is indicative of things like sort of mid-range heating sources inside the layer.
Right.
The challenge is that in terms of the number of photons we have.
Well, in principle, you don't care where the heat is coming from. As long as you have the post-outburst, a small scale.
Oh, yes, although there's one other aspect of this that is, I mean, there's so many systematic errors to worry about.
Yeah.
The post-outburst stuff, when it's really, really cool, the problem is if there is an accretion component to it, then that could mess up the spectrum rather
Well,
significantly.
we know that there is this non-thermal component in the spectrum.
It's going to be dominant, in fact.
But whether that's accretion is another matter.
Right, but it's not what you would expect from emission just boiling up from deep. And, so,
I couldn't tell about that.
and there are also short time scale variations and other things that are at least not with your simplest issues. So this is the reason why there is as yet no killer method you can absolutely trust. But a lot of these are advancing, and I'm hoping that there's going to be some concordance at some point.
Curious about the current state of atmosphere codes. Are they more limited by not knowing what physics to put in, or are they limited by they know the physics but computing whatever is hard and you have to think sometimes certain
For static stratified atmospheres, which is, believe it or not, what we're dealing with here, because a burst that lasts seconds is still many thousands of dynamical times. I think that the work that has been done by Suleimanov et al. Is pretty good. It does take a long time to compute in order to converge the accuracy they require, so it's not possible to trivially generate large tables of many compositions and these sorts of variations. When it actually comes to the burst itself, there are a lot of uncertainties about how the thermonuclear runaway exactly proceeds and so on. But luckily, that's unlikely to be important because the processing through the last few optimal depths is what's going to give you your spectrum. I think it seems to be in pretty good shape.
Okay, why don't we continue the conversation upstairs with the rookies? We're going to take polls